Now let's try to repeat the analysis of this data, pilot plant investigation, and try to repeat everything that I showed you in the videos. And you can see that this is the table that I have. We learned how to generate this table, most of it, in the previous video. And what you need actually to do, you need to fill in all these tables. So if you are not in my class, if you watch these videos and not one of my students who got this table actually directly, you can just simply pause this video and fill in this table. Just be careful to fill in everything correctly and then come back. Okay. Now I have all these response values. It means that I can just load all these values in from this Excel table. I call it pilot plant, and then do the analysis. Okay. So you can see that I already clear all the environment and the console. I have source DOI tools to get all the functions that we have written so far. And what else I need to actually to have library read Excel, because I'm going to work with the Excel sheet. Read Excel. No, I don't need the quotes. Read Excel. And then I load the data, right? So say D equal to read Excel. And then this pilot plant XLSX, right? And then you remember that by default read Excel returns what is called a table, and I would like to work with data frame. It's a little bit simpler. So I convert my table to a data frame. That's the second thing. Okay. And there is one more thing that you need to do. If you open this D, you can see that, for example, the temperature is a numeric values, and the concentration is also numeric values, and the catalyst it's a character values. However, when you do ANOVA, and we are going to do ANOVA, right? So you need these three values as factors. So let's convert them from the beginning. So let's say that we have D dollar temperature as a factor. D dollar temperature. We can do it faster by having special code, but in this case, I just want to be maybe a little bit simpler. Not very efficient, but simpler. So this like. And then also finally D dollar catalyst, right? Catalyst as factor. D dollar catalyst. Okay. So if I run this, and you can see now we have the factors. Okay. Now what else I want to do? I want to get design metrics separately. I want to separate design metrics from D. I can do it by having by using function subset. I simply say subset D. And I'm not going to subset any rows. I'm going to subset only columns. So I can just write select. And since all columns of interest, they actually line in a sequence. So I have to select these three columns. I can just write it like this. I say select all columns between temperature and the catalyst. Okay, like this. And I don't need quotes because these are kind of variable names. So if I run this DM, then you can see that indeed in DM I have only the design metrics, Then I can also write response. It's not necessary, but let me do it. I just save response values also separately to a vector. Okay. Now we are ready for analysis. And before we do ANOVA, let's compute the effects. Let's learn how to compute the effects. Okay. Well, luckily you can do it easily if you make this coded value. So let's make design metrics in coded values. Luckily we have this, and we have already the function that does it for us, right? So DMC, you can see these are the coded values. Now the idea is following. If you want to compute the main effect from the temperature, you simply need to multiply these values to these values. And you can see when it's low, it will be minus. When it's high, it will be plus. And then you take a sum and divide to the half of this number of rows, which is 8. That will be the main effect. It's exactly the same as we did in our calculations, but a bit simpler. So let me show you once again. So I take response, multiply it to the first column of DM. So this is the, not DM, DMC, of course, right? Look, this is minus, 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 minus. These are all levels. These are all outcomes where I have a low level of temperature. And this is plus, 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 plus. And then if I take a sum, all pluses will sum up together, all minuses will sum up together, and then you have sum of all pluses minus sum of all minuses, right? So that's the overall idea. And then you divide it to 8 to get an average. So strictly speaking, if I say sum of this and divide to 8, I should get 23. You remember that was the effect on the temperature, and I got 23, right? You can see it here. Okay. Now let's generalize it. again. So let's think how to make it more universal, more versatile. Well, apparently instead of 8, I know that there is 2 replicates in this case, right? So what I need to do, I need to divide it to a half of the number of rows. So I can say that divide to number of rows in DMC, but not all rows. I need to take a half of them like this, right? So that will give me the, not number of rows, now n row, it's called n row. That will give me also 23, right? But again, the problem is that now we need to do it for every column here. And on one hand, I can use a loop. We already know how to make a loop and then how to take every column and so on and so forth. But in this case, I will avoid loops and make it in a more efficient way. And in this case, I need to recall the linear algebra. What do I have as DMC? DMC, it's the matrix, right? We can call it as a matrix. So we have 3 columns and then 16 rows, right? And then the response is a vector. We have like 16 values here. So what you can see, I can make a dot product of this matrix with this vector. So I can simply say DMC times this vector. It will not work, it will produce an error. Why? Because when we multiply a matrix to a vector, we need to multiply row of this matrix to values of this vector, right? So we multiply, take a row, and here we have columns. So what I can do, I can just transpose it. I can say transpose DMC and multiply to resp. Now look, I got all the values simultaneously. So I don't need a loop anymore. Of course, I still need to divide them to 8 to this number, right? So, but we will do it in a minute, okay? Likely in R, there is a function that does it in a more simple way. It's called cross-prod. So if you write cross-prod, DMC and resp, you can see I got an error. And the error is because DMC is not a matrix, it's a data frame, and cross-prod requires a matrix. So I can simplify as matrix like this. So it will convert it to matrix first, and then you can see I got the same result here. Okay. Now I can simply write it, remove this one and say effects equal to cross-prod. And then I also need to multiply to this one, to divide to the number of, like this, to half of the row numbers, right? So if I do it like this and then show you the effects, you can see I got the effects all at once, exactly the effects that you saw before, right? Maybe this one is a little bit ugly, so I will add a call names here, call names, effects, and then I will just say effect, okay. Now, how to produce effects like this, okay. Let's try again. Now it works. Now, you remember, these are only main effects. Can we do the same for the interaction effects? Well, apparently we can. We need the CMC matrix for that, right? The contrast matrix. So I can say that get contrast matrix, DMC. And then if I replace DMC with CMC here, look, I will get the interaction effects. But how to do all together? Well, we can do it in a simple way. So I can say I can create a new matrix, AM, where I simply combine these 2 matrices together. I say cbind, DMC and CMC. So it will combine all columns of these 2 matrices. And then I will simply produce this AM, analysis matrix. And now look, this 6 lines of code does everything. So we get the matrix of the all interactions, except, of course, 3-factor interactions, which we know that it's noise. So we're not interested in that. And now we can actually write it also as a function. You can say get effects, and then function. We need both response values, let's call it dy, and then dm, the matrix, the original matrix, the design matrix. And then everything else will be done inside this function. So first we compute the coded values for this design matrix, then we compute contrast matrix. We combine these 2 matrices together. We compute effects by multiplying columns of these matrices to the response values and take a sum. This is what we use cross-prod for. Then we divide it to number of rows, half of the number of rows. And then we do some cosmetic changes, and then we need to return it, right? Return effects, okay? So now we have another very useful function in our toolbox. So let's move it there. So I just move it there, again here. And I do the same. So first of all, I clear everything. I click source to make sure that everything works. So you can see all these functions are here. And then I can just try it. So I say effect equal to get effects. And then I need to say resp and dm, and then show the effects. And you see it works perfectly well. So what's the next? The next is to make a main effect plot, right? Remember, we already have the main effect plot. Let me show you this main effect plot function. It's here. But you remember that we made this function quite versatile. We have also a lot of extra things like confidence intervals and so on and so forth. And we use like a 2-sample t-test to compute confidence interval. And we found out that actually it will not work in case of full factorial design, because when you do this based on the 2-sample t-test, you also incorporate all systematic variation to this estimation of noise, right? So what I want us to do, I want us to simplify this function a little, and then do a little bit extra. How to simplify it? I just want to get rid of all elements related to computing of error bar. So I take this one, standard deviation, number of values, t-value, error margin. I don't need this, so I just remove it. Then this one is also no more needed, because actually we don't have any error margin, right? So let me do it this way. So I say that ylim will be defined as a parameter of this function, so it will be defined here. And here I define it as follows. I take a range of y values. So range, it means mean and max, right? So by default, the limits for y will be the range of y values, okay? And of course, because I specified here, you can always provide your own values for the limit. So let's keep it like this, okay? Now what else? We don't need arrows, because that was we use for error bars, right? So we just do it like this, yeah. Okay. Now let's check if it works actually. So first of all, I save it, and then I go back to my code, and then I try to run it, right? So you can say plot main effect. Then you can see I need to provide y values, it's my response, and I need to provide one of the factors. So I say dm, for example, temperature, right? Then you can see that it doesn't work. It says invalid xlim value. So something is wrong with limits for x. Let's go there and see why we have this problem. And this is why. You can see that the limits, it's unique values of x. Yeah? What's wrong with unique values of the temperature? You remember that temperature in our dm matrix, it's not a numeric vector anymore. It's the factor with 2 levels. You can see it's 160 and 180, and it's a text values. So if I say unique dm temperature, you can see that it's not the numbers, it's actually the text values. So I cannot use it to make the limits for x. How we can solve this problem? Well, because we make this function only for 2 levels. And it means that you always have 2 levels, so you always have 1 and 2 for the factor values. I can actually use 1 and 2 for the limits, right? So I can say instead of this one and instead of this one, I can simply say xlim C1 and 2, okay? But that gives me another problem, because in this case, if I let me just remove this, and then also use 1 and 2 here, right? C1 and 2 here, these are coordinates of x. Also here, it's a segment, we also use coordinates of x, 1 and 2, right? So it will work this way, no problem. So let me show you that. So first of all, save this, go back, and then we need to reload this, so it means that I have to run this one again. So I will run the whole script. Then you can see that I forgot to remove ux in one more place. Let me see this one, right? So let me just say if length of unique x is not 2, then we have this trouble. So let me try again. Look, it works. Now it works, no problem. There is a little issue here. I don't have the 160 and 180 here. Although the temperature is 160 and 180, I don't have them anymore because I use the level numbers. It's the first level, it's the second level. How we can solve this problem? That's how to do that. Well, first of all, you still can have these unique values. Let me get back to the unique values of x, but now it will be unique labels, right? So it's not numbers, it's labels, right? And then I can use these labels here. And now this is a little trick. So first of all, I say make this plot without x-axis. So I say x-axis, axt equal to n. It means don't show the x-axis. Let me again show you the result. So you can see that now I don't have x-axis anymore. Yeah? And now I will make it artificially. I'll say at axis, 1 means it's x. So it's first axis, second, third. You can also have axis on top of the plot, on the right part of the plot. And then I say, okay, what ticks you should show? You should show 2 ticks at position 1 and 2. C1, 2. So again, let me save it and show the result of this, right? So you remember that before we didn't have any x-axis at all. Now if I run it, you can see that I have exactly the 2 ticks, 1 and 2, right? But I don't want to have 1 and 2 here. I would like to have labels. So label 1 and label 2. Luckily, I have labels already here. I saved them, right? So you can say labels of the ticks. Get from these unique values of x. Okay, let's check it. I got exactly what I wanted, 160 and 180. What else we can do in this case? We can also adjust the limits. You can see that maybe this one is too close here and this one is too close here. So maybe instead of 1 and 2, I will take a little bit smaller here and a little bit larger here. So the limits for x, I will define them as following, as 0.75 and then, for example, 2.25. And to let user, for example, myself, redefine these values, I will just cut this, write xlim here, and define them here at the beginning. So say xlim equal to, like this. Okay, good. So let's check if it works. It does. You can see it's a little bit more narrow. You can adjust it if you want, if you think the margins are too big, but it seems to be working, right? So I can also change the label, for example, xlab equal to temperature. C, and then you can see that it works, right? I can also change the label for y equal to, for example, the yield in milligrams, and it also works, right? Now, what about the main title? Well, first of all, you can see it's empty. Although I have this parameter main, I forgot to use it in my previous version of this code, so I don't have any main title at all. But let me do the following. Let me define the initial value for the main title as null. So it means no main title at all. So it will remain null if you don't change it. And now I actually add it here, right? So I say main equal to main. But because it's by default, it's null if I don't change it, if I don't provide it, right? So let me check it. So you can see it remains empty. But if I provide it, let me just do it like this. For example, main equal to main effect. Right? So if I provide it, it will appear. So main effect. Okay. Now let me remove it. So I don't have any title anymore. Now my point is that if I don't provide any main title for my plot, I will show the effect, the estimated effect here. And this is how to do that. I say if main is null main, this function is null, returns true if it's there is null in this, nothing in this, right? And I say if it's null, then main is simply, you remember that effect is simply average, difference of these two average values. So I say m2 minus m1, like this. Okay, and let's check. Now we have exactly the number here, so it's 23, right? And then let's check if it works for other two columns. So the catalyst 1.5, and you can see it's of course in this case I need to change the label as well, right? And then the concentration, you see it works, right? There is only one issue, is that I need to do a lot of plots manually. So I have to copy paste and then change these columns and so on and so forth. So which again, not nice to have, right? Let's write a function and let's call it plot main effects that will show all main effects together, right? This is how to do that. Well, first of all, you remember that we should show as many main effects, as many columns we have in DM. So we need to make a loop. So say for column goes from 1 to number of columns in DM, right? And then I simply do the following. So I need this function. I need DM, but only column number call. And I actually can define the labels as just the name of the column, right? So instead of this one, I use, for example, let me just remove all the rest like this. And instead of this one, I say call names, DM, and then number, again, call, right? So that's the little function I have. Let's see if it works. So if I run it, you can see I always have the last one because it made 3 plots, but the next plot is actually made on top of the previous one. So what I can do actually, I can say have enough place for all plots. So I say mf row equal to C1 and then number of columns in DM, right? So you can see that if I do it like this, now I have all plots together. Yes. What else I can do? I can actually do the following. You can see that I calculate number of columns 2 times, this one and this one. So let me use just n factor equal to number of columns in DM. And then I just, this is not necessary, but it's a kind of a nice things to do when you're coding. Like this. So check if it works. It does, right? Now let's make it a function. So let's call it plot main effects. Not effect, but effects. And then it will use the same 2 parameters, resp and DM. And then it will do this. Okay. However, look, in this case, I didn't specify the labels. I didn't specify the Y label. I didn't specify the main. I didn't specify other parameters that actually we can use for the main effects. But luckily, we can do it in a simple way. As you can see, like this, and then 3 dots here. And then when I call main effect, I also can add 3 dots here. So what does it mean? It means that if you have any additional arguments, they will be proxied to this function. Okay. So let's check it. Let's first of all move it to DOI tools. So save it. Let's move it somewhere here. Okay. Plot main effects, save it. And then let's try it. Plot main effects, resp and DM for a while. So first of all, I clear this, and then I run everything. And it seems like I have some problems. Let me check. I forgot to make it a function, sorry. That's it, like this. So try again. Now it works. You can see I will clear this one just to make it a more clear experiment, and then you can see it works very well, right? But now I can also say, for example, while up equal to response, let me use yield in milligrams, right? And then if I run it, you can see that I got the while up everywhere. So it seems to be working, right? Okay, the next point is to write a function that makes the interaction plot. And first of all, we will make a function which creates interaction plot only for 2 factors, right? And then we will make a more versatile function. So let's do that. As usual, I will start not with a function, but with the code. Apparently, what we need to make, it will be very similar to main effects plot. So let me just take the main effects plot function, and I will use it as a basis, okay? So this is a plot main effects. Let me take it. So we'll use it as a basis, copy, paste. And then I will remove all these extra things like checking if number of labels is correct, main. Let me keep this one for a while. Okay. Now, apparently, we don't have just x and y. We have 2 x's. One is the main factor, and one is the factors that can potentially have this interaction, right? So it means that I expect that there will be 3 parameters, y, x1, and x2. x1, it's the factor that I use also to make this plot, and x2, it's the factor that changes the effect of x1, right? So it means that I expect to have like 2 of main effects, right? Main effect from x1 when x2 is small, and then main effects from x1 when x2 is large. So that's the overall idea. So it means that I will have 2 labels. Labels 1, it's unique of x1, and labels 2, it's unique of x2, right? And then here, when I calculate this, let me define some values. So y will be just response, x1 will be the temperature, and then x2 will be the catalyst type. You remember we have the interaction between these 2, right? So we just run it and then check labels seems to be correct. Then this one. Yeah? You remember that instead of just having 2 mean values, we need 4 mean values. So we need mean when x1 is small and x2 is small, mean when x1 is large and x2 is small, and all the combinations of x1 and x2. This is how to do that. Right? Let's try it, and let's see what do we have in mean. And then I've also, let me remove this for a while. So now if you run mean and then look at this, you can see that we have all these combinations here, right? So this is the first factor. This is what we need to use for the x values. This is the second factor. It can be either a or b, and this is the values to make the plot for. Now let's just do it, right? So first of all, you see in this case, I don't need the second column, I need the third column for the means. So let me use this third column here. And then you can see that indeed I will get the means for the third column, right? Now, how to define an effect in this case? Well, first of all, let's split the mean values into 2 parts. So M1 is when the second factor is at low level. So it will be these 2 values, right? So say M1 and 2. And then M2, it's when M at low level, right? X2 is at low level 3, at high level 3 and 4, right? So again, if I run it, you can see M1, it's the first 2 values, and M2, it's the second 2 values, right? Now, how to define the effect? Effect, it's you take this difference minus this difference, and then you divide it to 2. That's how we define the effect, right? So this is what we are going to do here. So you say difference of M2, right? Minus difference of M1. So instead of just like this, and then I need to divide it to 2. So that will be my effect, interaction effect. Okay. What's next? Let me check that this works. I think I need to run it like this. We don't have main yet, right? So because it's a part of the function, so I will just run it like this. Main comes later, and you can see it's 10, right? It's exactly what we expect to see. And then you can see that to make a plot, I also need a lot of this xlim, ylim, xlap, ylap, and so on and so forth. This is what I use as a parameter of my function, right? Let me just say that xlap is just x1, ylap is just x2. Later, I will make them as parameters, right? Main is null. And then xlim, it will be the same, like for the main plot, 0.75, its limits for x and 2.25. Then ylim will be the range of y values, So these are default parameters that I'm going to use to make a plot. So let me run this. And then let me see what I do wrong. I forgot to write here. Let me just be consistent. It doesn't matter if you use equal sign or the arrow, but let me just be consistent and use arrows here. Okay. So I run this. Let's check that everything works. Now let's check that in main we indeed have the effect. Here we have. Now we make a plot. We add a grid. You can see that this is correct. These are not correct for a while, but we will check it. We will change it because y label should be y here, right? Doesn't really matter now. So now let's think how we can make this one. So remember that we make these 2 points and then we connect these 2 points with 1 line. But now we need 2 lines and 2 sets of points. First, we do it for M1. It's when the factor has a factor x2 has a low level. Right? Then you can see that, let me use, for example, blue here for a while. Blue. Okay. So let's do it. So this is it. Let me see why this one doesn't work. It's because I don't have this color yet. So let me also use blue here. I'll change it later. So this is the first line, right? This one. Now I need to make the same line, but for the 2 other values, right? So I see the same line, but for using the 2 means when the second factor is at high level. And then let me use red color here. Red color here. Red color here. Okay. Now you can see that I have these 2 lines, exactly what I wanted to do. Okay. Then I add the same label, the axis, but in this case I use labels 1, right? So this is the axis. So this is the temperature, and this is the effect of the catalyst on the effect of the temperature, right? One more thing I can add a legend. So you can say legend, and then let me add it to this corner, to the top left corner. So say top left. And the idea is following. I add a legend. I say, for example, the labels. It's the So in this case, I can say it's paste 0, x2, and the, for example, equal to, and then the combination, the labels 2, right? Then I can say color equal to blue and red. And then how to show the labels, let me use this PCH16. It's the same points that I use in my code. So you can see that, let me see, labels, paste 0. I think it should be legend, not labels. Okay, legend. Here we go. Now it should work. So you can see indeed we got a legend here, nice legend here. Now let's make it a function, and then let's improve this function gradually. So first of all, let me define this function here. So I can just say that this is, let's say, plot interaction effect, interaction effect. So it's one effect only. And then I say y, x1, x2, and then I will make all these labels, right? So xlab is equal to x1, ylab is equal to y. Then the main is null, the main title is null, and then xlim, and then I have ylim, and that's it for a while, okay? Here, now we open the function body, and then we have everything this inside the function body. Like this, and then close the function body. So now we can run it to load this function into our environment. And then you can see that I forgot to make it a function, so that's why it's function like this. And then I will change this so I have a little bit more space here. And then it's also very important that when we define the function, we should use these equal signs here, right? So that's it. Here we go. Now I think we will be able to load it. We did. So now you can see we have this function here. Yeah. Now we can try it. For example, say plot interaction effect, response dm $temperature. Let me use some other, for example, concentration, and run it. And then you can see we got exactly, this is the effect. This is the representation, the visual representation. So it works as it's supposed to, right? Now let's make a couple of additional improvements. First of all, you can see that I have two factors, so I have two names, right? So for example, this one can be changed by using xlab parameter, right? So I have xlab parameter. But how to change this one? So I need extra factor here, right? So let me make an additional parameter. I call it factor names. And by default, it will consist of this x1 and x2. x1 and x2. And now look, what I want to do, I want to change this one. Instead of this x1, I say it's the first factor name. Okay, so that's one thing. And then look, xlab, I already employ xlab here, but this second factor name, I can employ it here instead of this one, right? So I can just say factor names 2 here, right? So let's see how it works. So again, I will just, I'll just click source, and you can see that I got all the default factors, so that's okay. And now I can provide the factor names. For example, I say factor names equal to C, and then the first factor, it's a temperature. Let me use shortcut like this, okay? Then you can see it works. So now we have C here, and then we have T here. So now it's getting better. Then the final thing is that these colors, right? So you can see that by default, I have this red and blue colors, and then I keep repeating myself. So say red, 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 blue, 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 and so on. And also in this way, I cannot redefine the colors. Maybe you don't like this red and blue colors, and you want to use, for example, green and yellow, right? So let me also change this. Let me make color as a parameter. So I say like blue and red. So it's something that you can change if you want. By default, it's blue and red. And then I simply just change, for example, blue, it's color number 1. Color number 1. Color number 1. And then red, it's color number 2. Okay. And then instead of this one, I can just write col. Okay. So now it's, again, more versatile. So again, I will just do the following. I will check that it works. Maybe I need, oh, I think I made a mistake somewhere, right? Oh yeah, it's just C, of course. It's a combination, right? So let me try again. It works, right? So now let me just try to change the colors. Let me say color equal to, let me use, for example, cyan and green, just for an example. Again, click source, and then you can see it's indeed cyan and green. Horrible colors, but at least we checked that it works. Okay. Now what we need to do, we need to take this, cut it from here, go to DOI tools, and add to our toolbox. You can see it's getting large. It's more than 100 rows already. So we have everything here. Save it and check. And you can see it works indeed. Okay. That's it for this video. And in the next video, we finally will do some ANOVA analysis.